The theory of conservation of momentum, which is what we're looking at now, is just the same as the theory of conservation of energy. What did conservation of energy tell us?
Energy can be created nor destroyed.
Perfect. And that's what conservation of momentum is going to tell us also. The momentum before equals the momentum after. Okay, and there's going to be different scenarios we're going to look at in types of conservation for momentum, but generically, or generally speaking, we're going to be looking at momentum earlier equals momentum at the end.
Wait. If you start from rest, it's created.
Yeah, it's still going to be zero, yeah? And that's the crazy part. We'll talk about that in a moment. It's a good intuition you're thinking of already.
So momentum cannot be created or destroyed.
Correct. And we're on the next slide. It's right here, okay? So what we're saying really is the same thing we said with energy. Remember how we had MEI equals MEF? Now we have PI equals PF. The momentum of the system initially is equal to the momentum of the system at the end. So Ed asked a really good question. That's where I like to start this problem usually, and start this thought process. So what if two objects are at rest? What's their momentum together? Zero. Neither of them have velocity, right? So who wants to be two more demonstrators? Two more demonstrators. Reese, Mike, come on up. Sorry, Maria. Saw the hands first. First two. All right. So, Reese and Mike, all I want you to do is stand together facing each other. Okay? Yes. Not that close now. What I want you to do is this. I want you to make believe you're on an ice skating rink. And this is something you could try in the wintertime to prove that this is true. Okay? And they're currently both standing still in the middle of an ice skating rink.
Holding hands.
And they're not holding hands. And Reese says to Mike, hey Mike, push off, or like give me a push. So Mike decides to push Reese, and Reese starts to slide back. Well, if Mike's on ice skates, what's going to happen to him?
He's going to go back.
He's going to go back also. So Mike starts moving back. So let's use our conservation of momentum to describe what's happening. Let's come back together. All right, currently, are they moving?
No.
So what's their overall momentum?
Zero.
Zero. And we said that momentum is conserved. So momentum is zero now. It's got to always be zero between just the two of them. So when Mike pushes on Reese to push him back, and Reese starts going and Mike does, what can you now say about their individual momentums?
Very different.
Balance each other out.
They balance each other out.
But they're different.
But they're different in what sense? That they are,
Opposite.
yeah, opposite directions.
So won't I go farther though?
Well, let's talk about this now. And this is the next thing to talk about. They're clearly not the same weight, so they're not the same mass. So let's say hypothetically Reese is taller. So I'm going to say Reese is a higher mass than Mike does. So if Reese has more mass than Mike does, that means that when Mike pushes off Reese, Reese is going to move slower and Mike will move faster. So his velocity will make up for his lower mass. His higher mass will be made up for with a lower velocity. But in the end, they'll be equal and opposite one another. So let's say the mass of one object was 6 and the velocity was, he's going left, so say -8. That's going to be 48, right? But if his mass, instead of 6, is 8, now his velocity is only going to be 6 going that way. So because he had a higher mass, he'll have a lower velocity. He had a lower mass, he'll have a higher velocity. And those momentum will be equal and opposite of one another. So a system can start at 0 and remain at 0, provided they move in opposite directions with opposite momentum values. Does that make sense?
Yeah.
Okay, next guys. What is another analogy you can think of? What's another example of this exact same thing, where something starts with no momentum, okay, no momentum, and suddenly it's moving, but there's still no momentum? Who likes to play like Call of Duty or Halo or any of those games?
Water slides.
Okay, that's just my hint. That's the hint. Think about those games and what could be an example of something that starts with no momentum and suddenly has a lot of momentum. What's that? Okay, a bullet. You're on the right track. A bullet could work. I heard something else also. How could a bullet work? Hold your answer for a second.
Well, I guess explosion happens.
Okay, so when you fire the gun in the game, right? And you shoot, the bullet gets launched with a certain velocity and a mass. So what do you have? What's that called?
Recoil.
Recoil. They're still equal and opposite momentum. The momentum of the bullet going out of the muzzle is equal and opposite of the momentum you feel back in the recoil. That's why when somebody fires like a shotgun, the bullet is so massive that you're shooting and with so much force that you feel that recoil is much harder than if somebody shot like a sniper rifle with a smaller bullet.
You shot a
Okay.
shotgun before?
No, I'm just saying, hypothetically speaking, we've all played the games, right? Where in Halo, you shoot the shotgun, the gun kicks back. Nick, what was your example? What is it? Come on, you said it a minute ago. It was the one I want to hear. A grenade. Think of, a grenade is the best example. A grenade, you pull the pin, it's on the ground. Is there any motion at all? Assuming obviously you came to rest, so you can throw it, there's motion. But assuming a grenade, you pull the pin and you put it on the table. There's no momentum right now.
So you would be dumb if you do
What's that?
that. You are very close to that.
Obviously, I wouldn't do this in real life, folks. But say a grenade is here and you pull the pin on it. There's no momentum because it's at rest. And then suddenly, shrapnel is going in every direction. How is that possible if conservation momentum is true?
There's like a fuse inside or something.
Alright, there's a fuse
A
inside.
cell phone.
There's no shrapnel going in the equal and opposite direction, so they all cancel out.
Yeah, so how many pieces of shrapnel are getting exploded? Many, right? Hundreds maybe? So every little piece has a counterpart that's balancing it. So imagine like a piece of shrapnel this way, one piece this way, one piece that way. All of their components, and you have to break it into X and Y now. We're not going to do it in this section. We're going to do only linear momentum. Okay? But every piece is getting balanced by a different component of a different piece. So the system, that's the idea of a system, the system as a whole still has a momentum of 0. Even though each individual piece has its own momentum. They end up canceling one another out.
That way explosions always look like perfectly round.
I guess that would be a good answer, yeah. Because there has to be some pieces in every direction. So you see that like, almost like that mushroom effect. Yeah, absolutely.
We'll say Granada.
Now, for two objects colliding, take a look at this equation, please, and make sense of it. Momentum of object 1 times the velocity of object 1 initially. Mass. I said momentum. Mass of object 1 times velocity of object 1 initially. Mass of object 2 times its velocity initially. That's before. That's this right here. Then the momentum after is the momentum of object 1 times the velocity final. I said momentum again. Mass of object 1 times velocity final. Mass of object 2 times its velocity final. Okay, so as many objects as we have that many parts to the equation. We're only going to look at examples with two objects and linear motion. So it'll simplify it a little bit. But realistically speaking, think about like a hockey puck coming in at an angle, hitting another hockey puck, causing it to move. We'd have to look at the angle there, cosine and sine, to find the x and the y values of each of those. Okay, but again, we're going to just do head-on collisions. One-dimensional linear momentum. Let's take a look at the first example. A hockey player swings his hockey stick with a mass of 1 kilogram at a hockey puck with a mass of 125 kilograms. He swings the stick, grams, thank you. He swings, 125 kilograms would be ridiculous for a puck. He swings the stick with a velocity of 40 meters per second. And after the collision, the stick speed is now reduced to 30 meters per second. And that makes sense. Who plays hockey or baseball here? When you collide with the object, what happens to your object?
It stops.
Yeah, it slows down. Whether you notice it or not, it definitely does. A baseball pitch comes in, you swing the bat. The minute the ball hits the bat, it's slowing your bat down. You're pushing against it and you're overcoming it, but it's still slowing your bat down. So the hockey stick speed reduces by a factor of 25% here.
Is that like at least in baseball, I know it's having hockey, like the sweet spot of the bat, like because you feel like less of the.
Well, the sweet spot of the bat reduces the vibrations that are sent down the axis of the beam. That's what's happening there, really. But that's a little more different with vibration. We're going to do vibrations this year, though. So when we get to that, we can discuss. So again, the stick speed reduces. If the puck is initially at rest, what is the velocity after the collision of the puck? Okay, so we've got a lot going on here, and our subscripts get really messy. So you need to make sure you're being cognizant of what you write for each of these. So first, what do we want to call object 1? The stick or the puck? It doesn't matter. The stick, all right. It's the first one listed. So the mass of object 1 is 1 kilogram. The mass of the puck is 0.125 kilograms. Okay, notice 0.125 because it's 125 grams. So those are the masses, and they're not going to change. The masses aren't changing this problem. Okay, the masses are not changing this problem. A grenade, though, the mass would change, wouldn't it? You would say the mass of the grenade initially times the velocity initially equals the sum of all the little pieces of the grenade after the explosion. But here we have a stick and a puck, and the stick is not breaking. Okay? Now, we have an initial velocity of the stick. So we'll say V1I. Okay, be careful. V1I is 40 meters per second. And then V1F is 30 meters per second. So the stick goes from 40 meters per second to 30 meters per second after the collision. The puck is initially what? The puck is initially...
It's at rest, so it's 0 meters per second.
Very good. So V2I is 0 meters per second. And we're looking for V2F. Okay, so you can simply go ahead and plug into your formula. And if you forget what the formula is, simply list how many objects you have before and after. Which of the objects is moving before the collision occurred? Which is moving before the collision occurred?
It's the stick.
Only the stick, right? So our equation of M1 V1I plus M2 V2I, this whole thing drops off because there's no puck movement initially. So all we're going to plug in for is the first part. You don't have to worry about this because the puck is not moving. But afterward, they're both moving. The stick and the puck are both moving. Now, this is one of the few times this year that I'll tell you if you would like to. You don't have to solve algebraically. You never have to. But I usually recommend that you solve algebraically. And I still do recommend it. But if it confuses you because of all the subscripts and you want to go ahead and plug in numbers, that's fine. Okay? Because I know that last year a lot of students, they didn't make mistakes on the actual ideas, but they would get confused with their subscripts of what goes where. Because there were so many I's and 1's and F's. Okay? But again, this is M1 V1I. M2 V2I, M1 V1F, M2 V2F. It's always going to look like that when the two objects collide and then separate.
125 grams is, yeah.
I'm glad I could help. So let's solve for V2F if we did it algebraically. I'm going to subtract this entire term right here. I'm going to take this whole term and move it over to subtract it. So minus M1 V1F okay, so again, we subtracted this by bringing it over here. Now we'll just divide by M2. Okay, and that's our solution for the velocity of the puck. What do you expect? The change in velocity of the stick was 10 meters per second, right? It went from 40 to 30. So the change in the velocity of the puck must be what? What statement can you make based on thinking about logic right now? The velocity of the stick went from 40 to 30. It was reduced by 10 meters per second, the stick. So what could you say about the velocity of the puck? What do you expect?
I mean, it went from 0 to 10.
Or,
10 more than the stick.
Did we get transferred?
I wouldn't say exactly 10. There's one thing you're forgetting, Philip. The masses are different.
Oh, okay.
And think about hockey. If I swing a stick with a certain speed, the puck is going to end up going what?
Or the faster.
Yeah, faster or further, but faster really is the word. Because the mass of the puck is going to be much less than the mass of the stick. Okay? What do you get for a number here? What do you got?
80.
80 meters per second. Good. Okay? 80 meters per second. And I'm going to make a small note on the side here. I'm going to write it down, but then I want to talk about something. Some of you might notice it already. You guys, you have a question or?
No,
Make it real quick. Because the next one's really tough, this next problem. Go ahead, Owen.
Isn't it like 0.125 divide 10 by 0.125?
Yeah, that's exactly right. So what he's noticing right now is this. Take a look. The mass of 1 kilogram and the mass of 0.125 differ by a factor of 8. These differ by a factor of 8 when divided. Well, what was our change in velocity here for the stick?
10.
And what's the velocity change for the puck? What do 10 and 80 differ by?
So you're just
A
making
factor of 8. So it is proportional. It is indeed. Now, here's the thing. Here's the one thing. Sometimes the proportionality thing doesn't work out because we're going to have what are called inelastic collisions. So I would not go to proportions, and you'll see why in the next section. For today, if you want to think about proportions, it's good to know. But use the momentum theory, okay? I would not change the proportions right now. But I want you to see that it's not just a coincidence. Again, the factor of 8 occurs in both locations there. Reese, you okay? All right. I can tell. All right, let's go to the next one now. One soccer ball is kicked down the field and collides with another soccer ball that's at rest. Assume the soccer balls are identical. If the ball that is moving before the collision has a velocity of 12 meters per second east before it hits the other ball, and a velocity of 4 meters per second east afterward, then what is the velocity of the ball that was initially at rest after the collision? Okay, a lot going on here. So it might be useful to draw a picture. Here's the first soccer ball right here. It's currently moving with 12 meters per second east. It then collides into this other ball right here, and it kicks the other ball out, and then it continues to move after the other ball with a velocity of 4 meters per second east. So I kick a ball, it hits the other ball, it propels the other ball forward, but then it trails it with a velocity of 4 meters per second. We know that the original soccer ball that was moving has been reduced in speed. The other soccer ball is initially at rest, and we want to know what will its velocity be afterward. So again, we know that it's initially at rest. And we want to know what the velocity will be afterward. This is the initial velocity of the first ball. This is the final velocity of the first ball. Okay, so again, this is what's happening here. The balls collide, the second one gets propelled forward, the first one trails behind it.
Since the masses are identical, you can just drop the long frame.
Yeah, and that's what you're going to notice in the equation. Very good. So when you look at your equation here, go ahead and set it up. It's going to be the same beginning as we had last time. And what Maria is noticing is this. We said that the soccer balls are identical. So what is M1 and what is M2? Does it really matter?
No.
Because they're the... So you have M in everything now. See how there's all these subscripts? 1, 2, 1, 2. Technically I could do this. Erase, 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 and erase. Erase all your subscripts on the M's. Because they're the same. If it's a soccer ball with a mass of M, the other soccer ball has a mass of N. So if all of the masses are in all of these components here, we don't need them anymore. You can factor out an M on both sides or just divide everything by M and all the M's drop off. Okay, so this problem becomes very simple when you do that. And you can kind of remember this. It's not something you want to write down to memorize. But remember, when two objects have the same mass, and they collide, you can jump right to this line down here. Now, the second soccer ball was not moving initially, so that drops off. This had a velocity of 12. The final velocity of here was 4. So what will the velocity be of the other soccer ball? 8. Don't multiply, add. It's all right. Make sure you add there.
Wait, why did you erase the subscripts and then?
Because the two objects were identical, we were told. They're both soccer balls with the same mass, so I called them all M. Right? If they were 10, they would all be 10s, and they wouldn't have any effect on the problem.
Wait, so why didn't you just get rid of them?
Because we divided everything by M. Remember what potential energy and kinetic energy have? If you have M in every term, you can drop off.
Yeah.
Same thing goes here.
Yeah, so why'd you bother with the subscripts?
Just to show you initially. Yeah. What do you notice? What do you notice again?
Factor of 8.
Oh, that's a coincidence. Sorry. No, I'm sorry.
Oh,
But the difference in speed, look at the initial, the speed was 12 and then it went to 4. What's the difference there?
3. Oh.
Oh, sorry, no. The factor of difference is 3. You're absolutely right. But what is the difference in number, in numerical value? 8. It decreased by a value of 8 meters per second. Well, the second soccer ball went from 0 up to 8 meters per second. Okay?
So you
So
could
the
just-
momentum of the first soccer ball was transferred into the second soccer ball completely.
So you can just subtract, you don't need formula.
So in this one, it happens to work out that you could subtract. It happens to work out. Please don't memorize these interesting facts. They're good to know. You should know that in problems that are conceptual, you should be able to talk about them. But when you get mathematical problems, you need to start with your beginning line, please. Okay, because things can vary and things might change a little bit. All right? Okay. Let's look at example 3 here. Can I get a person to read this for us, nice and loud, please? Nice and loud, thanks, Elliot.
A person with a mass of 50 kilograms jumps off a platform with a velocity of 5 meters per second west. If he lands on a cart with a mass of 20 kilograms, wheels on the bottom that is initially at rest, what will their combined velocity be immediately after landing?
Okay, so right now we've got a person jumping, but then landing onto a cart. That cart's not moving. What's going to happen when he lands, though? They're going to start, hopefully moving together, and hopefully the cart doesn't, break or anything. So we've got a object and a separate object initially, but then afterward, what do you know about them? Yeah, they're combined as one object. So what would change about my formula now? Focus me. What would change about my object from before and after, and how would that alter my equation that we've been using?
You have an initial velocity of 0.
Okay, for one of the carts, good. That's not the question. The question was what would change?
Because you're jumping on.
Okay, but what would it change about the formula? Remember I'm saying, what does it change about the formula in the end?
Well, you have to add to like the latter portion of the formula, the MV1I, and the MV so I can obviously.
Yeah, just say it in words. Don't even worry about the formula. Just tell me in words, though.
Yeah,
What will
the
you?
first part of the formula to the second half because they're combined.
Yeah, they're combined masses at the end. So what we're going to have is this. This is what Nick's saying, but the subscripts get annoying. Initially, we've got this. Okay, now, afterward, the objects are merged together because it landed in there, right? So here's what it looks like now. And I don't need to specify the VF because they're together. If I jumped off this desk and landed on this chair and started sliding across the room, now we're one entity. Me and the chair would be moving together. We would have the same velocity. So there's just one VF. Okay? Again, you slide off the desk and land on the chair. Now you're merged. So this VF is the same velocity for you and the chair afterward because you're moving as one projectile. Therefore, you have to add the masses together because now you're like a fusion of two different objects together. Okay, so that's what would change about this problem here. Now, what do we know about the cart? Is it moving initially? So let's do that to start. Make it easy on us. And what are we looking for?
Final velocity.
Yeah, they're combined velocity. So let's solve for VF. So I divide by the quantity m1 plus m2. Remember, m1 plus m2 is a coefficient in front of VF. So just divide by it on both sides. Okay, if you want to, remember, put parentheses around here in your calculator when you do this. So you can go ahead and write it if you'd like. But again, you're dividing by this entire coefficient. You're moving it over here by dividing through. What do we get?
Velocity is going to be -5, right? Because
Correct. It's going to be -5 because it's west. What do we get for a number?
8.6.
Be careful.
Negative.
Negative.
What do you notice? Think about it logically. If I'm jumping jumping off with a velocity of, what was it, 5 meters per second, and now suddenly it's only 3.6. Why is that?
Because some of your velocity went downwards into the ground.
Okay, but imagine this is linear momentum now. This is linear momentum. So, here's the example. This person is running with 5 meters per second, and then this person just gets on the chair and starts sliding across. They're clearly not still going at 5 meters per second.
Like the time they're in the air, they lose.
The time what?
The short amount of time that they're in the air, they lose some velocity.
Okay, for sure, they do. That's realistically speaking, absolutely. What else though? What else is different about it? Phil?
Well, it's because, like, you're not in a frictionless world, so when you come down and it starts to go forward, friction acts in the opposite direction, so you don't go the same speed, you slow down because your mass.
Like what Reese said, that you're absolutely right. But what else? There's something else. You guys are definitely right. Friction does affect this. Something else.
Because the cart starts at the velocity of 0, with the swing your momentum, you get the cart moving.
Exactly.
So you slow down.
The cart is at rest, right? So part of your momentum goes into getting the cart moving, and then whatever's left keeps you moving. So you're like, suddenly you're just moving yourself, but now it's like running, right? And then imagine somebody just dropped 20 pounds on your back, and you have to continue running with that much weight on you. It would slow you down because now you have to pull more weight. It's the same exact thing. It's like a train car that has an amount of coal in the back of it. If there's like a certain amount of fluid and the fluid were leaking, you'd be losing fluid. Or imagine it's a snowstorm and the back of the train keeps filling with snow more and more. It's going to cause the mass of the train to increase, thus it would take more force to push it. If you kept with the same force, it would slow down over time because it's becoming more and more massive.
Why did you change the MI to 80?
Why did I?
That's a 50.
That's a 50, sorry. That's just me having bad handwriting.
Then it would be -8, not higher.
This is a 50 kilograms there, okay?
Then you would be equal to -8. No.
This is 50 plus 20. You got to do them together, so divide the whole. It's negative 250 over 70. That's all right. Yeah, if you subtracted them, it'd be over 30, and you would get the negative 8.3 there, yeah. All right, let's look at it. This is back to the first example we started with in the beginning. Two ice skaters standing together at rest in the center of the ice. They push off one another in order to move in opposite directions. So this was Mike and Reese before. If the mass of person A is 60 kilograms, the mass of person B is 40. The velocity of person B after is 7. What is the velocity of person A afterward? Okay, so what's their momentum beforehand? 0. So we could start by just doing this if we want to for this problem. Instead of writing M1 V1I, M2 V2I, just put 0 in the beginning. Because it's definitely 0. And that equals M1 V1F plus M2 V2F. Again, the velocities in the beginning are 0, so we'll just start with a 0 there. And now we can just simply solve. Okay? A and B doesn't matter. 1 and 2, same difference, right? So I'm going to solve for V2F. Okay, I'm going to solve for the second person's velocity. So I'm going to move this over, and I'm going to divide by M2. And then again, I'm dividing by M2. And that drops that off right there. Okay, and Elliot, proportionality holds true here, for sure. Okay, and you'll see that right away. So if we have a mass of, let's see, the first person is person, let's see. We're given the mass of person B and the velocity of person B afterwards, so those should go up here, since we're given both of them. We're looking for velocity 2, so that would come from person A. Okay, these need to be linked together. If you want to use A and B as your subscripts because it was given that way in the problem, you can. There's not really any difference at all there. So let's plug in. So we're going to have negative, and that's a 40 kilogram, times the velocity of 7 meters per second.
You just make one of them negative?
Over, no, I subtracted it, so.
Yeah, I know, but you just make one negative.
Yes, when there's a negative in front of a product, the negative just applies to one of them, really. What was the other mass? 60? Okay, Okay, so we're going to get 280 over 60, or 28 over 6, right? Negative. What do you got?
14 over
4.8.
4.6.
Negative 4.7 for rounding, yeah, negative 4.7. So this makes sense as to what we said before. Let's reiterate what we made as a conclusion earlier with Mike and Reese. The person is moving with 7 meters per second, and this person is moving with a negative velocity to balance. The person with less velocity had more mass. 60 kilograms was negative 4.7. They related, and the 40 and the 7 related to each other. Hey, what I want you guys to do, you don't have class tomorrow, but you do have class on Wednesday. You can definitely do this homework. There's one more example at the end. I'm going to record it. You're welcome to watch it. I recommend watching the last recorded one. Okay?